Hi, in this video we're going to talk about what duality means in the context of linear programming. Alright, so this diagram shows a maximization problem. Now you may remember what maximization problems, think of an example maximization problem. Suppose you're trying to maximize revenue and you're producing, say you're producing two different types of goods. Now in this case, the two types of goods would be represented by x1 and x2. Okay, all right. And then your limits, you also have a limited number of resources. Sorry? Or limited raw materials, you could say. And these limitations are represented by some numbers B1, B2, and B3. Okay, so suppose you have three raw materials that go into two goods, and you're trying to maximize the revenue. Right. So the revenue from good 1 will be C1, and the revenue from good 2 would be C2. Right. So that's the situation we have here. Now you can write equations to express this, and these equations are represented by these lines here. So we have three constraints here. This red line is a constraint. The equation is A11x1 plus A12x2 equals B1. In other words, for raw material B1, good x1 requires A11, good x2 requires A12. And you're limited by the total amount of raw material, so you have this constraint. Now the constraint actually is less than or equal to, but I'm just writing the equals because I know less than or equal to will simply be below this line. Similarly, we have two other constraints. This is constraint for the second raw material. B2 is the amount of the second raw material. And again, this is the amount used by good 1, and this is the amount used by good 2. So that gives me my second line. And I'm supposing I have a third line also. So three raw materials that give me three constraints. And what's known as the feasible region would be the intersection of the three half planes below these three lines, right? Because according to raw material 1, I have to be below the red line. According to raw material 2, I have to be below the blue line. According to raw material 3, I have to be below the black line. So I'm not going to shade it in, but that's going to be this region delineated by this point, this point, this point, this point, and the origin. Of course, we know that x1 and x2 have to be positive. Right? Now, we also have a revenue, and that's what we want to maximize. And the revenue is given by C1x1 plus C2x2. C1 is the revenue per unit x1, and C2 is the revenue per unit x2. I can also draw that as a line. So take a look at how these lines are situated relative to each other. The way you find the optimum is you slide this line, this objective function line, parallel to itself until you intersect this feasible region at the highest possible point. So this is the highest possible point. You can see that if I drew a parallel line through this point, it would be lower, and I would get less revenue. Right. Now, what is special about this point? So let me draw perpendiculars to these constraints. So this red is perpendicular, this line is perpendicular to the red constraint, this blue is perpendicular to the blue constraint, and this black is perpendicular to the black constraint. And the cyan is the perpendicular to the revenue line. Now notice something. In this case, the revenue perpendicular is bracketed by the other two. In this case, it's outside of the two perpendiculars. So this is in kind of inside. It's kind of within the, you could say, the positive span of this. It's actually called a cone. Now, what this means in terms of vectors is that this perpendicular vector is a positive linear combination of these two perpendicular vectors. And you can see that if you think about vector addition, I go along this blue line in a for a positive amount, and then I go along the red line for a positive amount, and I get this cyan line. I can't do that here. If I go along the black line for a positive amount, and then I go along the blue line for a positive amount, I can't possibly get to this cyan line. So this cyan line is not a positive linear combination of these two perpendicular lines. Now, what do the perpendicular lines represent? It turns out that these perpendicular lines are the gradient or rate of change of these constraints. Now, if I change B, what direction does the line move? The line moves perpendicular to itself, right? So you can think of it that way. The other way of thinking about gradient is it's the vector of derivatives. If I take the derivative of the constraint with respect to x1, then that's a11. If I take the derivative with respect to x2, that's a12. a11, a12 is exactly this perpendicular vector that's perpendicular to the constraint. So you can think of the gradient as the maximal rate of change. If I go in this direction, then I'm going to maximize the rate of change of B1. All right? So I have a gradient for the constraint 1, the gradient for constraint 2, and the gradient for the objective function. So the gradient of the objective function is bracketed by the gradients of the two constraints at the maximum point. And it turns out that that's true in any number of dimensions, and that's what particularly characterizes the maximum point of this region, assuming that x1, x2, x3 all have to be positive, and these constraints are all less than or equal to constraints. Okay, so take a moment to think about that. That's the distinctive characteristic of the maximum point for this optimization problem. It distinguishes this point from every other extreme point of the feasible region. Right? So let's work out the implications of what that means. Notice something else from this picture is that at this point, the third constraint does not hold with equality. In fact, there is a slack. If I consider a31x1 plus a32x2, which is the left-hand side for the third constraint, at the third constraint is B3, but at this point, the value of a31x1 plus a32x2 is less than B3. So this third constraint is not operative. It doesn't hold. So it has what we would call a positive slack. All right? So positive slack means that the linear combination of the gradient has no component of this third gradient. Okay? So you can see here that positive slack means zero contribution of the gradient. So this is kind of a duality between variables. If this slack variable is positive, then this variable here, this contribution variable, is 0. All right? So let's write this out in vector notation. At the maximum point, as I said, C1, C2, which is the gradient vector, or the vector perpendicular to the objective function, is equal to a positive linear combination v1 a11 x1 a12 plus v2 a21 a22, all right, where these are positive. That's important. Okay, I can write this as two separate equations, C1 and C2. All right, then I can add these together. Remember, this is what I'm trying to maximize: C1 x1 plus C2 x2. Right? If I add these two together and I substitute what is C1 and what is C2, I get this. Now, if I rearrange, what happens? Well, if I group the terms on the left-hand side here that have v1, what do I get? I get v1 times a11x1 plus a12x2. What is that? Go back up here and you'll see that those two terms simply comprise b1. Right? So I have this first, the terms, if I pull out the terms that involve v1, I get v1 times b1. If I pull out the terms involving v2, I get v2 times a21x1 plus a22x2. What's that? That's exactly b2. Right, so you get this dual relationship between these x variables, which are the variables that locate the maximum point, and these dual variables v1 and v2, which tell you how to get the gradient of the optimization function in terms of the gradients of the constraints. All right? So the duality is between points, locations, and gradients. Right? So that's the relationship. And gradient is rate of change. So you've got this kind of back and forth relationship. And I could do the same thing for a minimization problem, and you'd get a similar result. All right, so let's try to describe this using linear algebra. We have vectors, so linear algebra is a natural mathematical language to use to describe this situation. All right, so let's consider only the constraints that hold with equality at the maximum point. That is b1 and b2. So we're looking at the maximum point up here. Let's go up a little bit. Okay, here's the maximum point here. Two constraints hold with equality, the b1 and the b2, and they have the corresponding gradients here and here. All right, now, how would we express these constraints in terms of linear algebra? Now, these are two equations, two unknowns. And if you've had linear algebra, it's well known that two equations, two unknowns can be expressed as a matrix equation with a 2 by 2 matrix of coefficients, a column vector of variables, and a column vector of constants. So that's what we have down here. The constraints that hold give us this system of linear equations. Now there's one constraint that doesn't hold. I'm going to leave that out. Now, as I mentioned, when you have a constraint that has slack, you leave out that variable and it doesn't come into the calculations. All right? So at the optimum point we have ax equals b. All right? Now we also had an expression for the gradient in terms of the two gradients of the constraints. You have this gradient of the first constraint, gradient of the second constraint. And we said the gradient of the objective function is a positive linear combination of these two gradients. So that means C1, C2 is V1 times this plus V1 times this. Now actually that's again a system of two equations and two unknowns. The C1 is V1A11 plus V2A21. C2 is V1A12 plus V2A22. We've written that down here, I believe. Right. All right, now, it's convenient to write these two equations not in terms of column vectors, but in terms of row vectors. We can do that just as well as with column vectors. So we can write it this way. V, which is a row vector of unknowns, of variables, times A, which is a matrix of coefficients. It's the same A that I have here. That's why we write this as a row vector, so that we can use the very same A. So this row vector times this matrix is equal to the vector, the gradient vector for the constraint. All right? Ax equals b, VA equals c. All right? Now, what are we trying to optimize? We're trying to optimize C1x1 plus C2x2. Now, in terms of vectors, that's just the same thing as the row vector c times the column vector x. This should remind you of matrix multiplication. That's exactly what it is. If you write this out as a row vector c times column vector x, you'll see that that's what this quantity is here. All right? So what is Cx? Well, C is VA, so I can write this as VA times x. Now I can reassociate my terms, and group the a and x together. But if I group the ax together, that gives me b. So that's why I have cx equals vb. I can write the same quantity in terms of the position unknowns x or the gradient unknowns v. So there's your duality. Those two quantities are the same. All right. Now, when you talk about the duality, you use an inequality. Let's see how that works. Suppose I have some solution x prime to ax prime less than or equal to b. That would be some point in the interior here. That would be some point below. Right? In that case, I can write ax prime as b minus epsilon, where epsilon is a non-negative vector. Right? If this left-hand side is less than or equal to the right-hand side, that means I can subtract something from the right-hand side and get the left-hand side. So, and since this is left, that subtracting vector is a non-negative vector. I'm reducing b to get this side here. All right, so let's multiply cx prime. All right, cx prime. Now remember, c is the same as va, and I can reassociate, so that's vax prime. Now x prime is exactly b minus epsilon. Okay, so that's vb minus v epsilon when I distribute the v, because I can do that in matrix multiplication. Now, since v is positive and epsilon is positive, this inner product here, this multiplication of row vector v times column vector e, is positive. So I've reduced vb by taking x prime instead of x. That means x is optimal. It maximizes cx for all x's that satisfy this inequality. On the other hand, suppose we have a solution v prime to v prime a is greater than or equal to c. I can use the same strategy. Since va prime is greater than or equal to c, that means I add something positive to c to get v prime a. So v prime a is c plus epsilon, where epsilon is a non-negative vector. I can do the same thing. Suppose, so if I want to find v prime b, which is the dual quantity that I'm optimizing, I replace b with ax, and I reassociate v prime a. V prime is c plus epsilon. The cx plus ex. Now x is a non-negative vector, so this ex, epsilon x here, is also non-negative. So I've increased the value of the optimization function. So that means v is optimal. Remember, cx is the same as vb. All right. So we see the dual relationship between the system ax less than or equal to b and va greater than or equal to c. There's a dual relationship there. And the optimum of this problem using the cx optimization function is the same as the optimum of the minimum problem where you're using vb as your optimization function. All right, let's talk a little bit more about what v means. V has the following interpretation. Suppose I increase or decrease any component bj of b by some amount delta j. All right. So think of what b means. B is your resource limitations. Up here I talked about b was your raw materials. So suppose I increase b by any amount. Now notice if you increase b3, nothing's going to happen. You're still going to be optimized here because b3 is not your limiting value. If I increase b1, then that means shifting this red constraint up a little bit along this gradient. If I increase b2, that means shifting this blue constraint along this gradient. And in both cases, you can see that this cyan point is going to shift. It's either going to shift along the blue constraint if I increase the red, or it's going to shift along the red constraint if I increase the blue. But in any event, if I increase either one, if I increase b1 or I increase b2, I'm going to get an increase in my objective function, which is cx. What is the magnitude of this increase? Well, let's see how that works out. Okay, so suppose I increase or decrease in component bj of b by some amount delta j. And this is delta j is positive if I increase, or delta j is negative if I decrease. As long as the constraints remain the same, That is, as long as I'm still limited by the two same constraints b1 and b2, it follows the objective function will increase or decrease by Vj delta j. So why is that? Because I've increased Bj by delta j. That means that this Vb has been increased by Vj delta j. And since the gradients haven't changed, the gradient of the constraint hasn't changed, the gradient of the objective function hasn't changed, so that's all the same. So my objective is just going to be the same V times B plus delta B. So my objective has increased by this much. So you can say Vj is what you'd call a marginal benefit. Marginal means like derivative. It means like with a small change. If I make a marginal change in the amount of resources, then Vj gives me the marginal rate of increase that change incurs. All right? So that's a very practical interpretation. Okay. Now it works the other way as well. If I have a minimization problem and I increase or decrease any component Cj by delta j, the objective function will increase or decrease by Cj xj. So here xj represents the role of a marginal cost. If I increase the requirements, when you have a limiting cost problem, you have some requirements. You have to attain some certain level, but you want to minimize cost. If I increase the levels that I need to achieve, it's going to cost more. How much more? Well, if the increase in my requirement Cj is the delta j, then the increased cost is going to be Cj delta j. So you see that it works both ways, and you have a practical interpretation for all of these quantities, both the x and the v, and the b, and the c. So take a little while to think about this. It's worth your while to understand thoroughly the situation that we're looking at here. Okay, that's it.